So thank you, everyone. Lillian, I'll just ask if there are questions in the chat, if you can read them to me. For some reason, yeah, it's hard for me to see. Okay, so and also please let me know if it fails to advance like it was yesterday, the slides. Okay, so today's lecture is going to be, well, there'll be two parts. For most of the lecture, I'll be speaking about Master's theorem, which I stated last time, and I'll remind you what it says. And this will be very different in method than what I've been doing so far. This is going to be something that's purely in commutative algebra. So this is going to be showing that the existence of an auxiliary polynomial gives us the desired result that we want, and it's going to be sort of something that holds very generally in fields of characteristic zero. It doesn't have these analytic techniques. The analytic techniques went into getting to the point where we could apply this theorem. Right. And then the second half of the lecture, I'll speak on some ideas, maybe ideas is too strong a word, some wild speculations about how we could hope to go beyond Waldschmidt's theorem and Master's theorem. That's something as I mentioned, I'm interested in because of the extensions to Leopold's conjecture, and I'll tell you some sort of vague ideas I've had in this direction, and hope it strikes something into one of the, either one of the grad students that has energy to work on this in a way that I haven't, or in one of the experts that knows something that I don't, because I'm very far from being expert on these things. So I think there's lots of open problems for research, and I'd like to stimulate some of those. Okay. So all right, so let's remind us what Master's theorem says. So Master's theorem starts with a field of characteristic zero, and we have some n by n matrix of non-zero elements in this field, and we define x and x of n as before. So what were these? So x was just the set, sort of the subgroup generated by the xi, okay, inside of k star to the n, right? So this is x1, x2, all the way up to xm, okay? And so xi is the ith row of this matrix, okay? And then x of n was sort of the box, sort of, and this is with, so x1 to the a1, dot, 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 xm to the am, okay, with 0 less than or equal to ai less than or equal to n minus 1. Okay, so where this is just this multiplication is happening inside this group. So you think of it as component-wise multiplication of vectors. Okay. All right, so we define a pairing on z to the m cross z to the n. This is a bilinear pairing that we defined, which took a tuple of ai's and a tuple of bj's, and just take it to the product of xij to the ai bj. And then Master's theorem is that suppose for some capital N greater than 0, which you imagine to be large, that there exists a polynomial such that the degree is maybe smaller than you expect it to have the vanishing property I'm going to mention, which is that so the degree is less than capital N to the power of m over n divided by some constant, and that it vanishes on all the elements of this box, okay, this x of n. Then the conclusion that you want to make is that there exist subgroups of these spaces, z to the m and z to the n, that are large and orthogonal, so that a dot everything in a dot everything in b under this pairing is 1, where the rank of sort of the proportion of the ranks that you get in total is greater than 1. So m prime over m plus n prime over n is greater than 1. Okay, and right, this can be easily seen to be translated into the result on matrices that I unexpected visitor. Well, the result on matrices that I stated before. So Waldschmidt's theorem got us to the point where this polynomial exists, and then Master's theorem is going to get us to the final conclusion that we want, that after a change of basis, this matrix has a big chunk of zeros in the upper hand corner. And as we saw, this gives us sort of the best theoretical evidence towards Leopold's conjecture, which is that the Leopold rank is at least half of what it's expected to be. Okay, so here is David Masser. Okay. All right, now I'm not going to be able to prove the whole theorem actually today in details because it would take longer than a 1-hour lecture. So what I do want to describe in detail is the very simplest case of this. In this case, the algebraic geometry component of it is basically Bézieux's theorem. And so in this way, we can view Masser's theorem as a higher rank or higher dimensional version of Bézieux's theorem. Okay, and that's, I think, the right way to view what Masser's theorem is. So let me do this simplest case using Bézieux's theorem. So the assumption now is that, so in this case of 4 exponentials, so my little m and my little n are 2. Okay, so what is the assumption of Masser's theorem? It's that there exists a polynomial of degree less than capital N over 2, such that p of z equals 0 for all points in this box x of n. Okay, and the conclusion, I'm going to state it in a slightly different way. I mean, so it's sort of simpler to see what the conclusion is in this small case, is that it suffices to show that x of n has fewer than n squared elements, right? So xn is sort of indexed by n squared elements, that is the elements, the a1, right? So this is x of n. This is the set of x1 to the a1, x2 to the a2, where a1 and a2 take on n values. So this is indexed by n squared values. If the set has size less than n squared, that means there's some equality of 2 of these elements for 2 different ordered pairs, a1, a2. Okay, that means that x1 to the a1 times x2 to the a2 is equal to x1 to the a1 prime times x2 to the a2 prime for some distinct pairs a1, a2 and a1, a prime, a2 prime, a1 prime, a2 prime. And if that holds, then it's easy to see that the conclusion that we want holds. That is, that gives you sort of either a row or a column of zeros in your matrix after some change of variables. So maybe I'll leave that as a slight exercise, which it's very simple, to show that showing that this is smaller than you expect it to be gives you the conclusion of the theorem. Okay, so let's suppose for contradiction that we have such a polynomial and yet this has the full size that it could be of size n squared. Let's see what we can deduce from that. If we start with any z in x of n over 2, so a box of sort of half the size, and we consider a shifted polynomial in a sense, which is that you just do a change of variables on your variables x and y, you scale them by this z1, z2, and you make that your new polynomial, which you call q sub z. Then this q sub z vanishes on x sub n over 2 because the original z was an x sub n over 2. If I plug in xy and x sub n over 2, then you're just multiplying vector-wise, component-wise, z1, z2 by that xy, which lives in xn over 2, and sort of x sub n over 2 times x sub n over 2 lives in x sub n, right? It just sort of, you just add the exponents. So if they each live in x sub n over 2, then their product lives in x sub n. Okay, so q sub z vanishes on x n over 2, as does your original polynomial p, of course, because p vanishes on all of x of n by assumption. So each of these polynomials, qz and p, vanish on this. Their common zeros contain the set x sub n over 2. Okay, but how big of x sub n over 2? How big is x sub n over 2? Okay, so it's as big as it can be because we're assuming that x sub n is as large as it can be. So x sub n over 2 is contained inside of it. It has to be as big as it can be, which is n squared over 4. So qz and p intersect in n squared over 4 points. Right, so we have these curves in the plane, and they intersect in n squared over 4 points. But the degree of p is less than n over 2 by assumption, and the degree of q is obviously the same as the degree of p. Just look how it's defined. It's just a multiplicative change of variables on the variables. So it has the same degree or at least the degree doesn't go up. Okay, and so that implies that degree of p times degree of q is less than n squared over 4 because they each have degree less than n over 2. Okay, now this would contradict Bézieux's theorem unless there was unless they share a common factor. So if these were didn't have any component in common, then their intersection of these two curves of degree n over 2 can't have more than n squared over 4 points. So that means that we know that for every z in x of n over 2, that this translated polynomial qz has to share a common factor with the original polynomial p of xy. Okay, so let's see how that can happen. So let's say that the factorization of p of xy is into these irreducibles, fi of xy. Then the factorization, of course, of this is just changing variables. So the translation is just you translate each of the irreducible factors. Okay, and we're saying that for each z, these two share a common factor. So that for each z, there exists an I and a j, such that fi of z1x, z2y is equal to some scalar multiple, okay, of some fj, some other irreducible factor of this p. Okay, so how many pairs ij could there be? What I want to show is that there's two different z's that give me the same pair I and j. But how many irreducible factors can there be? So the number of pairs ij is just the number of irreducible factors squared, right? The number of fi's is the number. Fi's are the irreducible factors. It's just the number of irreducible factors. Well, the largest the number of irreducible factors could be is the degree of this polynomial. So the number of pairs ij is less than the degree of this polynomial is n over 2. So the number of pairs you could have is n over 2 squared, right? It's less than n over 2 squared because the degree is less than n over 2. Okay, but n over 2 squared, remember, that's the size. That's the number of z's that we're taking. The number of z's that we're taking is where z's are indexed by x n over 2. So the number of z's is n over 2 squared because we're assuming this has maximal size. So by pigeonhole principle, there exist two different z's that give me the same ordered pair ij. That is, there's two different z's, so z1, z2, and z1 prime, z2 prime, that have the property that fi of z1x, z2y equals some scalar, so that the scalars will be different possibly, but times fj of xy, but the I and j will be the same. Okay. And what that means is, you can see very clearly, easily, that means that f1 of z1, fi of z1x, z2y has to be a scalar times the same I, fi of z1 prime x, z2 prime y, for some scalar lambda and distinct z1 and z2 prime, z1 and z prime. Z and z prime. Okay. All right, so that's just combining the two equations. That fi, the equation for z gives me fi of z1x, z2y is equal to scalar times fj of xy, and then times a scalar, and then the same equation, and then you just combine those two equations and you get this. So this is a different lambda that showed up than we showed up before, but some scalar. Okay. Now, the fi's are not monomials. This is pretty easy to see. First of all, they're irreducible. So if they're monomials, they would just be one. It would either be x or y. But the point is, there's no point of having a factor of x or y in our original polynomial. Our original polynomial was, the whole point of it is just that it has small degree and it vanishes on all these tuples. So multiplying it by a non-zero scalar, the x's are never 0. So multiplying it by x doesn't help you. So you can just divide out. If your original polynomial is divisible by some x or y, you could just divide out by that x, and the new polynomial would have the same property and even lower degree, in fact. So there's no advantage to starting with a polynomial that's divisible by x or y. So you can assume that fi is not equal to x or y. I think actually if it is x or y, the same argument works. But anyways, since they're not monomial, it has at least two monomials in it. Okay, and then you just write down what you get. So, okay, I don't know if I should write this out, but somehow, so if one monomial here with some coefficient. It doesn't really matter. The coefficient is going to cancel on both sides of this equation. But if I think of one monomial, say x to the a, y to the b, then I'm getting that z1 to the a, z2 to the b times x to the a, y to the b equals some scalar times z1 prime to the a, z2 prime to the b, x to the a, y to the b, because I have an equality of polynomials. I'm looking at the x to the a, y to the b term. So there'll be some coefficient, but then I'll cancel that. And of course, you can, in fact, just cancel the entire, variable part of it to get an equality of two numbers that you care about. And I said it's not a monomial, so there's going to be at least one other monomial. So there'll be some other equation like this with C's and D's, and it will be the same scalar lambda, right? Because it's just an equality of polynomials, and it's one scalar that's equating the two polynomials. Okay. And then by dividing these two equations, then you get an equation of the form that I just wrote, which is, so the lambdas will cancel when you divide the equations, and you'll get that z1 over z1 prime to some power y1 times z2 over z2 prime some power y2 is equal to 1 for some non-zero pair of integers y1, y2 in z squared. Okay. So what this says, if you think about it, is that you can do a change of basis of your matrix so that it has at least one zero. So taking the logarithm of this equation. So remember, we're trying to conclude that you can do a change of basis, a rational change of basis. So this is sort of a rational change of basis. We want to show that you can do a rational change of basis that there's an entire row or entire column of zeros. And what this tells us, if you look at what this says, if you take the logarithm, you get a 0 here. And it tells you that if you do a rational change of basis, so that's why it's important these y1 and y2 are integers, that you can do a rational change of basis to get at least 1 0 in your matrix. Okay. All right, but your matrix has determinant 0, so once you have 1 0, then it has determinant 0. There has to be another 0 either in the same row or the same column. Okay, so that's kind of it. I think you can beef this argument up a little bit, so you don't even have to assume that the matrix has determinant 0. You can actually just produce the other 0, but let me not get into that. Anyways, so this is the conclusion of the proof of Master's theorem in our very special case that we have a 2x2 matrices. So the algebraic geometry that is input here, you see, is just Bézou's theorem. Okay, so now let me, in the next chunk of time, give some of the details, a lot of the details, but not all the details in how you do the general case. Okay, so use the same idea that I've used of this group action. So you have sort of x of n. Well, I guess, yeah, x of n is not a group, it's just a set, but x is a group. And x, right, so x is a subgroup of k star to the n. Okay, and you can let it act on the polynomial ring by acting on the variable. So the same idea is used. Okay, and just a bit of notation. This is I've used several times. If a is in z to the m, then we're going to write x to the a as the corresponding product of xi to the ai. Okay, so this is an element of x, right, just contained in k star to the n. Okay. Now, for each prime ideal of this polynomial ring, we're going to define the stabilizer in X of P to just be the set of elements in Z to the M, okay, such that the associated element of X, X to the M, stabilizes the prime ideals. So this acts on the ring, so therefore it acts on the ideals of the ring. So we want, if it stabilizes, we're going to call it the stabilizer. But we're going to view it, instead of being as a subgroup of X, we're going to view it as a subgroup of the elements indexing X, namely these tuples in z to the m. Okay. So here's the sort of a key lemma. So look at the maximal ideal of R that corresponds to the point 1, 1, 1, 1, 1. Okay. And suppose I have a prime of height n prime, and let A be the stabilizer in this in X of P. So this is some subgroup of Z to the M. Okay. Then if giving a large stabilizer, right, so then we want, right, if you have a large stabilizer, then you want to know that you have these kind of orthogonal subgroups. So this is kind of giving us the conclusion that we want. So then in this case, there exists a subgroup B of Z to the N of rank greater than or equal to whatever the height is of this prime, such that A and B are orthogonal. So this is how we're going to prove the existence of our A and B. We're going to construct a prime ideal of height n prime and a subgroup B sorry, we're going to construct prime ideal of height m prime such that its stabilizer, excuse me, has rank at least m prime, where, right, so then we'll try to find P of height n prime and okay, such that the stabilizer of xp has rank m prime. Sorry, this is hard to read. This is why notability is a little bit better. The pen is better. Where the condition that we want to satisfy, m prime over m plus n prime over n is greater than 1. So that's going to be our goal then, to apply the lemma by constructing a prime with a large height and a large stabilizer. Okay, and large means m prime over m plus n prime over n is greater than 1. So that's going to be our goal, is to construct this this prime ideal. Okay, so let's prove this lemma. Okay, and we're going to use this. We're going to use this Vandermonde trick again that we saw in Baker's theorem. Okay, so what is the B that we're going to take? Right, so let me just go back to remind you, really remind myself what A is the stabilizer. Okay, so we want to construct a B. So let me tell you what the B is. B is going to just be the orthogonal elements. So we said we want A dot B to be 1. We're going to just define it to be the set of things that are orthogonal to A. So A dot B, or by dot I mean this inner product here. A is orthogonal to B by definition. B is the set of things orthogonal to A. And now we just choose a complementary lattice in Zn. Okay, so of course, not every subgroup of Z then splits off as a direct summand, but it does if you tensor with Q, right? So once you tensor with Q, this B is some finite dimensional subspace, so I can choose a complementary subspace and then intersect that with Z to the N, I get some Z. Okay, so we want to show that the rank of Z is less than or equal to n minus n prime, which means, because then that implies that the rank of B is greater than or equal to n, right? It's greater than or equal to n prime. Okay. Okay. So now let Z1 through ZS be a basis for Z. Write Zi as a vector, Zi1 through Zin. Then we're going to consider, the corresponding, we're going to think of these as exponent vectors. So remember, Z is contained in Z to the N. So then I can take my variables on my polynomial ring and raise them to this power. Now these might be negative. I'm allowing them to be negative. So I need to consider a slightly larger ring than R, where I've inverted the TI. So I call that R prime. Okay. Now this is, what is it called? A Laurent polynomial ring. This has transcendence degree n. Now P by definition has height n prime. And one of the equivalent definitions of height, if you remember from algebraic geometry, is the height is the transcendence degree of over k of the fraction field of the quotient. Okay, so the height, so the transcendence degree of the fraction field of the quotient is n minus n prime. Okay, so what does that mean? If the transcendence degree is n minus n prime, if s were greater than n minus n prime, we want to show s is less than or equal to n minus n prime. If s is greater than n minus n prime, that means that there's an algebraic dependence because the transcendence degree is just n minus n prime. So we know that there exists a non-zero polynomial q with coefficients in k such that these elements, right, these s elements, I have s elements, u1 through us, so they have to be algebraically dependent because they live in a field of transcendence degree that's less than n minus n prime, and s is greater than n minus n prime. Okay, so then we know that there exists a polynomial, so the q of u1 through us vanishes inside r prime mod pr prime, which is to say that it's in p times r prime. To say that it's 0 and when I mod out by pr prime, to say that it lives in pr prime. Okay. All right. All right. So then each ui is a expression in terms of the t's. Remember, it's product of t's to some power. So then think of that as a polynomial in the t's again. There's a Laurent polynomial. Okay. So q prime in t1 through tn. And then remember we have our action. So for any a in z to the m, we have x to the a, which is an element of x, and that acts on q prime. Okay, and now by definition, remember x to the a stabilizes p, right? That was what capital A was. It was the stabilizer of the prime ideal p. Okay, so that means, and q prime is in p, so that means that x to the a q prime is in p. Okay, and p is is contained in this maximal ideal m. That was what p was. It was some prime ideal contained in the maximal ideal corresponding to the point 1 1 1 1 1, right? Which means that this polynomial, if I plug in 1 1 1 1 1, I get 0. That's what the maximal ideal corresponding to the point 1 1 1 1 is. It's the set. It's the set of polynomials that vanish at that point. Okay, so q prime of x to the a times 1 1 1 1 is 0, which is to say that q prime of x to the a is 0. Okay, and if you go back into the definition of what this x to the a is and how we define this inner product, this is saying that q of the inner product of a with z1 dot 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 a with zs is equal to 0. Okay, so now I'll fix a and apply this with a replaced by all of its multiples for d equals 0, 1, dot, 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 dot. Okay, so dA just raises these to the dth power. So q of, oops, it's hard for me to q's that aren't bold q's. All right, q of, right, dA z1 x comma da, da, da. This is a bilinear pairing, right? So this is q of a z1 x to the d comma da, 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 right? So this is just raising all the arguments to the dth power. So then again, now you're saying you have a polynomial that vanishes. So then writing out the monomials that define that polynomial and making a matrix, and then saying that I have all these roots where it's just the original root, and then to the power, raising all the components of the vector to the dth power for lots and lots of d. Okay, then right, and I know I have this for dA for all a because it's a subgroup, right? This capital A is a subgroup. This was for anything in the subgroup, so I have this for all d. In fact, I have infinitely many d. Okay, then I have this matrix, and I can make it a square matrix by taking the correct number of d's, which is a Vandermonde matrix. Okay, and so saying this polynomial exists says that there's a kernel to that matrix. There's a column you can multiply it by to get 0, which means the determinant is 0, but that's a Vandermonde determinant. Okay, and so that what that means is that right. So what that means is that there's two different sort of a dot zi's that have to be equal. So a dot their difference has to equal 1. Okay, so that means that a dot w in this pairing is 1 for some w that is a linear combination of this, a non-zero linear combination of the zi's. I shouldn't have said it's just two different z1s, because you're taking all monomials in these, right, when you make your matrix. So it's some monomial and some other monomial. So it'd be a dot sort of two different monomials in the zi's equals 0. So the a dot their difference is some arbitrary linear combination, some non-zero, however, linear combinations of the z's. Okay, and the size of each of these coefficients is less than or equal to the degree of w, the degree of the polynomial q. Okay, so therefore a is, so this was true for any little a and capital A. And what we've shown is that for this fixed set S that I've defined, this fixed set S, that a is orthogonal to some w. Okay, so a lies in the orthogonal complement of w as w ranges over S. But this S is finite, okay? And a finitely generated abelian group cannot be written as the finite union of proper subgroups. So these are all subgroups, and I'm saying that A is the finite union of these subgroups, okay? But a finitely generated abelian group cannot be written as the finite union of proper subgroups. Therefore, one of these subgroups has to be all of A. Okay, so that means there exists a W and S such that A dot, the whole group A dot W is 1. Okay, but that means that W is orthogonal to A, which was the definition of B. B was the orthogonal, was the set of elements that was orthogonal to A, right? And so that, so that means that W is in B. But where did we start? We started, we had our W as being some linear combinations of the Z's, and Z's were a basis of Z, and Z was a complement to B. So it can't lie in B and Z at the same time unless it's 0, but it's not 0. Okay, so that's a contradiction. Okay, so the only thing we assumed to get the contradiction was the existence of this Q, which we said by, that existence is because this S, the number of variables, is greater than the transcendence degree. So that can't have been true. So we must have S is less than or equal to n minus n prime as desired. Okay, so there's that lemma. Now, how am I?
Interesting. Here again, we see, like we did yesterday, the seemingly special role of the exponential. I mean, to me, you showed something had an inner product being 1, but you're always taking log to then call that orthogonal.
Yeah, I mean, it is a bilinear pairing, and so we're using the fact that the exponential function has the property that e to the a times e to the b is e to the a plus b. Yeah, so we're using some group action in a very nice way. I think you could generalize it if you somehow had a group action, right? The exponential function is naturally giving us a group action somehow.
Right.
Okay, great. All right. So now, as I already alluded to, this is now what the main theorem is that we have to prove. Now we have that lemma, which is, okay, so suppose we have this auxiliary polynomial, some polynomial in n variables, whose degree is smaller than you would expect to have this amount of vanishing, p of x equals 0 for all x and x of n. Then the conclusion you want to draw is that there exists a prime ideal of height m prime such that its stabilizer is large. So its stabilizer has rank m prime, where m prime and n prime satisfy this condition that you're looking for, right? And so what we've just explained for the previous lemma is that once you have that, you then have these orthogonal subgroups, A and B, of ranks m prime and n prime, where m prime over m plus n prime over n is greater than 1. Okay, it's because, right, that this subgroup, this stabilizer, has its orthogonal complement has rank n prime, where n prime is the height. Okay. So now we're going to sort of turn this around, do the contrapositive version of this. Okay. So for each n prime between 1 and n, let m prime, so this is really depending on n prime. This is This is sort of m prime sub n prime, but I don't want to clutter the notation. So let m prime, depending on m prime, be the maximal rank of the stabilizers as p ranges over all primes contained in this maximal ideal associated to the point 11111. Okay, with height equal to n prime. Okay, and then you define kind of a funny invariant. It's not clear where this comes from, but I'll just define it as so eta sub n prime. Okay, as you let p range over all primes inside the maximal ideal with height equal to n prime, you let m prime be the maximal stabilizer or such a thing, and then you define eta n prime to be this. Okay, I'll mention if any m prime equals m, then we're done, because then m prime over m is 1, and you just wanted m prime over m plus n prime over n to be greater than 1, and n prime is greater than or equal to 1 by definition, so n prime over n is greater than 0. So if m prime over m is, if m prime is equal to m, then we're done. So let's not worry about that case when I'm trying to define this variable, right, which has an m minus m prime in the denominator. Okay, so the point of this change of variables or this invariant is that what we actually want to show, or what we want to get, is that eta n prime is greater than n over m if and only if m prime over m plus n prime over n is greater than 1. So this is kind of an easy just manipulation of variables. This is an algebraic manipulation of variables. Okay, so here's the theorem. Let f have degree, so this is just the polynomial ring in n variables, have degree d, and let capital N be d to the eta 1 plus dot 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 d to the eta n. Then there exists an x of n such that f of z is not equal to 0. So this is the contrapositive version, right? Because it's what we said was, suppose there exists a polynomial of degree less than, so let me write this. So now suppose we have this theorem. So if there exists p with degree less than n to the n over m times 1 over n, okay, such that f of z equals 0 for all z and x of n, then right, so that can only happen by this theorem if some eta n prime is greater than n over m. Must have some eta n prime greater than n over m, right? Because if you didn't have that, if all the etas i's were less than or equal to n over m, then this polynomial would provide a contradiction, right, to this theorem. So then we must have some eta prime that's greater than n over m, and that implies what we want. Okay, so this theorem is sort of the contrapositive version of what we want to prove. So now we just have these invariants, these etas, and we want to show that there exists sort of some element of x of n such that if you take the group action on the associated element to our polynomial, then it doesn't vanish at that point. Okay, so now I want to introduce some notations. So we're going to let this capital Gothic M be sort of the translates under the group action of the maximal ideal. So this is the union of the maximal ideals associated to each of the points z. So this is sort of the set of polynomials that vanishes. So another way of saying this is the set of polynomials in R such that q of z equals 0 for some z and x. Okay. And then Sm, we're going to use this. This is a multiplicative subset. This is the complement. Okay. If q and q prime don't vanish on any points of x, then their product doesn't either. It's a multiplicative subset. So we can localize at it. And then for any ideal A, we define A star to be sort of the extension and then the contraction with respect to this localization map. So you localize at this multiplicative subset, you look at the ring, right? So this is contained in S R. You localize, you take the ideal generated by A in this localization, and then you intersect back with your original ring. Okay, so so what does this give us? What's the point of doing this? Which is that for a prime ideal, this P star, this starring operation, so A star always contains A. Okay, so that's sort of clear, right? But this starring operation doesn't make it any bigger if and only if P is contained in Z times M for some Z and X. So that's maybe I'll leave this as this is an exercise. This isn't completely obvious, but so the statement, and then and if it is bigger, then it's just P star is just trivial. So this is exercise in the definition of localization. Okay. It's not giving me the option to advance. Maybe if I swipe. Okay, there we go. Okay. And next, we're gonna want to use some invariants that come from the Hilbert polynomial associated to ideals, and that works nicely when you're dealing with homogeneous ideals in graded rings. So let's pass to that setting. So we adjoin an extra variable t0. So remember, I had originally my R was k adjoin t1 through tn. So now I'm going to adjoin another variable, t0, for the purpose of homogenization. And given any element of R, you can homogenize it. So you just pad it with enough power, each monomial, you pad it with enough powers of t0 to bring them all up to the same degree. Okay. So then you have a polynomial that's homogeneous. And so by the way, I should say that I'm using the proper definition of degree in this lecture. I have been, hopefully that's been clear, of sort of the sum of the exponents of the monomial, not the sort of simpler version that I used in my previous talks. I apologize if that was confusing. Okay, and for any ideal of the original ring, you let A0 denote the homogeneous ideal generated by the homogenizations of all the elements in that ideal. And then when you quotient, so this is a graded ring. Okay, graded by degree, and when I start with the homogeneous ideal, then the quotient is a graded module for that graded ring. Okay, so I just want to remind you that there's a polynomial called the Hilbert polynomial of A. So I guess you could call this the Hilbert polynomial of A0. It's really associated to A0, but we're gonna start with an A in my original R, which is just the inhomogeneous polynomials. What we're going to do is we're going to homogenize it to get this ideal A0, okay? And then once you have this, once you have a graded module over a graded ring, then there's something called the Hilbert module, which kind of records the dimension of the graded pieces of this, okay? So it's a very famous theorem, but there's a polynomial that's such for I sufficiently large, the dimension of the ith graded piece of this graded module over a graded ring is given by this polynomial. The dimension and degree of the original ideal are defined to be it's a little bit confusing because the dimension is the degree of the polynomial, and the degree is some scaled version of the leading coefficient of this polynomial. And the reason, why do we call it this? Why do we call this degree when it's the degree? The reason is that in the usual notion of ideal, if you start, right, so if A is just a principal ideal generated by some F in my polynomial ring, then the degree of A equals the degree in the usual sense, the maximal sum of exponents of any monomials appearing in the polynomial. The usual definition of degree, the degree is equal to the degree of that. So that's why it's called degree. Okay. So I'm going to include a slide that I skipped over in this presentation when I post them on the website to give you more properties of dimension and degree in case this has been a while since you've seen this, or if you haven't seen this. And those are used in the details of the proof, which I'm also going to skip over later. So I'm just going to spend a few moments now giving the general idea of how we finish off the proof of master's theorem. Okay, so sort of telling you all the ingredients and then telling you sort of a recipe, but then actually cooking the thing you can do on your own afterwards by looking at the slides. I'll have all the details of the full proof in the slides that you can look at later. Okay, so let's start with our polynomial f. Remember, so what are we trying to show? We're trying to construct some element z in x of n such that f of z is not 0. So we start with some polynomial d of degree d, sorry, that was our notation. And for r going from 1, not just up to n, but n plus 1, we're going to let n sub r be d to the eta 1 plus dot, 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 d to the eta r minus 1. And what we're going to do is inductively construct an element fr and a z linear combination of elements in that, and they're all given by our original f just translated. So it's kind of like what I did in my simple case, the 2x2 case, where I had these QZs, which are just translates of my polynomial P. In the general case, we're going to end up taking Z linear combinations of such translates. Okay, and we're going to take the ideal generated by these. So we're going to construct FR in each way. In other words, we're going to choose an element, some translate of F, and a linear combination of those, such that the ideal generated by F1 through FR satisfies either one of the following. Either AR star is, okay, this is running low on battery, so let me plug it in. Either AR star is unmixed of height R, either AR star is equal to R, the full ring. Okay, so then when I do this trick of extending and then contracting, I actually get the whole ring, or it's unmixed of height R and degree at most d to the R. So you probably don't remember what unmixed of height R is. At least I didn't know when I started reading this proof. So let me remind you. This ideal is called unmixed of height R if all of its associated prime ideals have a height R. Okay, so the associated ideals are the radicals of any ideals in a primary decomposition. So this is something that you may remember from commutative algebra, the primary decomposition of ideals in this polynomial ring. Okay, so this will give the theorem. Okay, so why will this give the theorem? Because if you look at the maximal case, when R, this will hold for all of these R's. So if you look at R n plus 1, AR star cannot have height n plus 1. Okay, there's no ideals of height n plus 1 in the polynomial ring with n variables. So that means the other case has to hold. So that means that an plus 1 star is R. Okay, and remember what I said. That means that if your contraction is R, this means that that means the original ideal can't have been contained in this this capital Gothic M. Okay, so that means that one of the ideals generating this ideal, so Fi, F1 through Fn plus 1, one of them can't live in M, because that's the definition of Gothic M. It's the translates of M. So in particular, right, it can't lie in M because this is the union of M and some other stuff. So in particular, it doesn't lie in lowercase Gothic M. And so remember what this Fi was. Fi is a linear combination. It's a Z linear combination, actually, of translates of our original polynomial F with the Zi's in x sub n sub eta plus 1. Okay, but if this doesn't vanish at 1, that means that F can't vanish at all of the ZJs, right? If F of ZJ, so if I plug in 1 to this equation, then I get Fi of 1, which I'm saying is non-zero because Fi is not in this maximal ideal. And on the right, Zj dot F evaluated at 1 is just F evaluated at Zj. And so if this is non-zero, then some F of Zj has to be non-zero. And that's what we wanted to prove. Okay. Okay. So that'll conclude the proof. So if we can construct these FRs inductively, then we'll be done. Okay, so this is all I'll say about the proof of this inductive construction, and I'll move on to the other topic after this. Okay, so there's 4 steps, and they're kind of done in detail in the remaining slides that I'm going to skip over. Okay, so for any associated prime ideal of AR minus 1, we show by counting that there exists some element in this set such that if I translate, it's not associated to AR minus 1 stars. That is, we know in terms of the degree, the number of associated primes of an ideal is less than or equal to its degree. That's one of the properties that I said I'll write on that earlier slide that I skipped. So it's less than or equal to its degree. So, and then we know how many elements are in this set. So just by counting, you can say that there's one that gives you a prime that's not associated. Okay. And because this group action works nicely, x to the negative AP is not associated to this ideal if and only if P is not associated to this ideal. Okay, so the fact that it's not associated, so this is basically like in Bezout's theorem showing that you can't have too many coincidences of the irreducible factor. So this is the step that's saying like, okay, Q, Z, and P can't share a common factor if I have enough Z's. So this was the pigeonhole argument that I used, okay? So you can't have, right? So if you have enough Z's, then you can't have every QZ sharing a common factor with P because there's only so many common factors P could have, which was its degree. And that's the exact same argument that's being used here. So I just want to point, everything's sort of much fancier in language, but it's just the analog of that exact argument, okay? So the degree is a more complicated notion of degree in terms of this Hilbert polynomial. Sort of the irreducible factors that's playing the role of the associated primes. So everything sort of has an analog. So that's why I wanted to do that example so you could understand what's really going on. Okay. So then you show that implies that there exists one of the ideals, one of the generators. That means that one of the generators of the ideal. So what is FR? So AR minus 1 is generated by F1 through FR minus 1. So the fact that that P is not associated to x to the AR minus 1 star implies that x to the A phi is not contained in P. That's easier to do. And then again, it's not hard to show from that there's a Z linear combination of these values that does not lie in any P associated. So for each P, I have some x to the A Fi that's not in it. And that means that there's some linear combination of them that's not in any of the P's. Okay, and then you let AR equal the ideal generated by AR minus 1 and FR. You've constructed it. You show that it has the desired property that either AR star is R or it's unmixed of height R. So somehow, each time you add one of these FRs, the height is going up by 1. Unless you get AR star equals R, in which case you're done, as I explained. Okay, so that's it. So that's all I'm going to sort of say about Master's theorem. So I did the 2x2 case in details with Bezout's theorem, and every step here is kind of, as I've explained it, is parallel to one of the steps that we did in that proof. Okay, and if you're very interested, as I said, so I'll swipe through them here. I go through each step 1 through 4 that I just described in a lot of detail, and this will be posted on the webpage when I post these slides. So in the last 5 minutes, I want to talk about something that normally would be too wild and speculative to speak on, but in a workshop like this where we're trying to use collective mind hive to generate ideas, I thought it'd be nice to talk about something that I'm completely stuck on, which is an attempt to prove Leopold's conjecture. The reason to not talk about it is just the embarrassment to say that you've thought about it, but right, you can't prove big results unless you think about it. So here's some idea. Okay, at least there's an epsilon of a non-zero idea here. So we want to go beyond Waldschmidt-Masser. So as I alluded to earlier, the thing about Waldschmidt-Masser is you can't try to prove that just from the vanishing of the determinant that there exists a polynomial of low degree that has all this vanishing. Why? Because the conclusion of Waldschmidt-Masser, which is this huge block of zeros, is just not true in general. It's not true that the determinant vanishing implies there's a huge block of zeros. You really would need the rank to be really small, like less than this. In the square case, it would be less than m over 2 to get such a big block to be 0. Okay. So I started wondering, what conclusion can you possibly draw just from knowing that the rank is, even 1 less than you expect or want, which is the full rank. So what can you conclude if you have a matrix, say a square matrix of logarithms of algebraic numbers such that the determinant is 0. And so I want to propose this conjecture, which I've never seen written in the literature, which is just that there's 1 0. That is, you can do a rational change of bases on left and right, not to get a huge block of zeros, that just get 1 0. There exists non-zero x and y, so integer, non-zero integer vectors such that the product in this pairing that I've defined is 1. In other words, to say in terms of the original matrix, so you don't need to introduce this notation, is just to say I can multiply by a column vector on the right and a row vector on the left that are rational and non-zero such that I get 0. Okay, that's the conjecture. So one interesting fact, so one thing that we proved, that this conjecture is implied by the structural rank conjecture, okay, and hence by Chanel's conjecture, as I explained. Chanel's conjecture, the special case of it, implies this by this theorem of Roy. So this is expected to be true. So that's one good thing. It's always nice to try to prove things that are expected to be true. So we expect this to be true. It's a nice exercise to prove this theorem, actually. It's not completely trivial. I'll leave it for you to think about how you might try to prove this theorem from the structural rank conjecture. Now, this conjecture is still deep. Okay, this is not so easy, and you can see that because in the 4 exponential, in the 2 by 2 case, when n is 2, it's very easy to see this is equivalent to the 4 exponentials conjecture. So this is still very much open and I think a deep result. We don't know how to prove the 4 exponentials conjecture. But one thing that's nice is that thinking about this in the general case actually gives insight on what you might try to do to prove the 4 exponentials conjecture, which no one else can do. So people have tried to construct this polynomial of low degree that has all this vanishing, and it's not been successful. I mean, I've thought about it, and I don't know how to prove it. But then thinking about the proper generalization to the n by n case, which I think is this one, leads you to think about what type of auxiliary polynomial should you really be trying to construct. We saw that in the general n by n case, you shouldn't be trying to construct a polynomial of low degree, because that would imply a huge block of zeros, which we don't expect to hold. So maybe you shouldn't even be trying to do that in the 2 by 2 case. So in the 2 by 2 case, the block of zeros and single zero are the same because it's so small. And so you don't see that you shouldn't be trying to construct this polynomial because it actually should exist. But in the general n case, it doesn't necessarily exist. So what should we be trying to construct? Okay, but before I say that, let me say one thing. This conjecture really is strong in that what I've been able to prove that it implies Leopold's conjecture. Okay, this is also not obvious, but this conjecture, which I call the matrix coefficient conjecture, that's what I call it. The p-adic version of it implies Leopold's conjecture and the Gross-Kuzmin conjecture. So it would be very nice. So if maybe we haven't done very much, but what we've done is sort of bridge the gap between the 4 exponentials conjecture and Leopold's conjecture. I think Leopold's conjecture for the higher rank case, people have tried to approach it through the full structural rank conjecture. And my hope is that this conjecture is weaker, is easier to prove. Okay, you just need 1 0. So how do we get 1 0? And it turns out to be enough. Okay, so the big question is, what kind of auxiliary polynomial should we try to construct? And my proposal is that, okay, if we have this matrix of logarithms whose determinant vanishes, then for n sufficiently large, I want to propose that there exists a polynomial with fewer than n to the n monomial terms that vanishes on x to the 2n. I mean, even if you prove x to the n, I mean, x of n, right? So x of n, right, generically should have n squared elements. So there shouldn't be a polynomial with fewer than n to the n monomial terms that vanishes on this set. Okay, because if you try to do it by setting up your matrix of monomials and plugging in your arguments and saying I want something vector, then you'll get some square matrix, and that square matrix generically shouldn't have vanishing determinant. Okay, but so what I want to propose is that if you have a matrix of logarithms whose determinant is 0, then in fact such a polynomial should exist. Right, so I think even if you put x of n here, this would be very amazing to prove, because even with just x of n here, then over R at least, you would get the 4 exponentials conjecture if you could prove this. Okay, so one thing we've proven is that over R or CP, this conjecture implies the matrix coefficient conjecture, the one that I stated 2 slides earlier, for n equals 2. Okay, And the same is true if you beef this up a little bit. So if I impose some extra conditions on the exponents appearing in this polynomial that's sort of sparse, if you will, or a fewnomial to name the language that others have used for these kinds of polynomials with fewer monomial terms than you would expect, given their vanishing. So if I pose some extra condition that it's a little bit technical, I don't want to write here, then in a argument similar to Master's, in fact, I invoke Master's theorem that you can then prove the result, the conclusion of the matrix coefficient theorem, that is, there's a non-zero vector x and y that you multiply, you get 0. So basically, I really think that this is the right. I could be wrong because I don't know how to prove it, but I think this is the right type of auxiliary polynomial you want to produce. A polynomial with fewer than the number of monomials you expect to get this kind of vanishing. Okay, but there's no control on the degree. So this is the point, the punchline. No bound on degree. I think bounding the degree by n. Okay. So bounding the degree by n, or if I say the degree is less than or equal to n, then of course that means that it has fewer than n to the n monomials. But I'm saying that the degree, bounding the degree, is too strong a requirement. Bounding the degree would give you this huge block of zeros, which we don't know exists. And what I'm saying is that if you don't bound the degree, you just bound the number of monomials, then you get exactly a condition that's equivalent to what you expect to be true, which is just that there's 1 0. And that's all you expect to be able to produce is 1 0. Okay. And so now that leaves me with the question of how to produce this polynomial with many roots that has few monomials. And I have no idea how to do that. I've tried and failed. So I wonder, if anyone in this audience has ideas, or has it ever seen anything like producing sparse polynomials with many roots, then I'd be very excited to hear about that. I can mention, even though I made this big hubbub about not bounding the degree, but bounding the number of monomials, you can do a sort of translation in terms of a polynomial of low degree, but it's not vanishing on this set anymore. But you need basically a subset of x of size n squared, size sort of a constant times n squared. You can do that by saying the existence of a polynomial is saying that this matrix of monomials evaluated at my parameters has a kernel on the right side. Well, then you can say there's a kernel on the left side and interpret that in terms of a polynomial also. So you can translate this into a statement about degree with different vanishing, or if you want this vanishing, then a statement about number of monomials. It's essentially equivalent. But either way, I have no idea how to produce such a thing, and I'll leave that as a tantalizing open problem. All right, thank you very much, and thanks for your attention during this entire lecture series. It's been a pleasure.